So in the quantum wave function, symbolized with psi, there are several variables. These variables could be x, y, z for Cartesian coordinates. They could be r, theta, and phi for radial coordinates. But they definitely include the variables n, l, m sub l, and m sub s, no matter what coordinate system is being used. And these n, l, m sub l, and m sub s are the variables in the quantum wave function known as quantum numbers. Recall that we can perform an operator on the quantum wave function. The Hamiltonian operator can be used to determine the energies of different quantum states, and that squaring the quantum wave function gives us the probability of finding an electron within a described volume. And that we use this probability, usually at, say, the 90% level, when we talk about the shapes of the orbitals. And so let's go ahead and take a look at n, l, m sub l, and m sub s. And n is the principal quantum number, or the shell number. And n can be any positive integer. In general, the higher the principal quantum number, the farther away from the nucleus the electrons are, and the principal quantum number is also the quantum number which dictates the energy of the electron to the largest extent. The other quantum numbers have effects on the energies of the electrons, but those effects are much smaller than for the shell where the electrons exist. The second quantum number, L, is the azimuthal quantum number, which is associated with angular momentum, but this is the type of orbital and L can be any number from 0 up to n minus 1. Again, sticking with integers. M sub L is the magnetic quantum number. This is the specific orbital, or the direction of the orbital. And m sub L can have values from negative L up to 0 up to positive L. This is associated again with the specific orbital and the direction in terms of which axis the orbital lies along, or which axes the orbital lies along. M sub s is the spin quantum number. This just specifies a specific electron up or down, and the values are plus or minus 1/2. Looking at all four of these, this is almost like thinking of an address. So you could be thinking of whatever scale you want to think about. If you want to think the smallest scale, let's say you've got a twin sibling and you and your twin sibling share a bedroom. And so the spin tells us whether you are in the top or bottom bunk. And the magnetic quantum number would tell us which bedroom you were in. The azimuthal quantum number would tell us the street number. And let's say the street. And then the principal quantum number might tell us something like the city. And between those four values, we can describe specifically where any one of a set of twin siblings is in that city or in that nation or on the planet. Okay? You can come up with other analogies if you like for these as well. But these are giving us more specific information about where those electrons are. But there are these rules for what values are acceptable. So in class, we've already gone over what the possible values are for the first and the second shells. On your own, you should have gone over what the possible values are for the third shell. And so this video is really going to cover what the possible values are in the fourth shell when n equals 4. So what are the possible values for L? What are the possible values for M sub L? What are the possible values for M sub S? What does that all tell us? And so for an n of 4, you can have an L of 0. You can have an L of 1. You can have an L of 2. And you can have an L of 3. So all of these L's, these range from 0 up to n minus 1. So these are the allowed values for the azimuthal quantum numbers. If L is 0, M sub L can only be 0. So this is a spherical s orbital, of which there is only one. So there is only one M sub L value for any s orbital, because the L of any s orbital is always 0. There's only an M sub L of 0 for an s orbital. However, this has two possible values for M sub S, plus or minus 1/2. When you look at the L of 1 in the fourth shell, just as in all other shells where there are p orbitals, there are 3 p orbitals, and their L values range from -1 to 0 to +1. And for each of those, there are 2 spin values. I'm not going to write all of the 1/2 fractions here. For a L of 2, this is a d orbital. And the M sub L's will range from -2 to -1, 0, +1, and +2. And again, for each of these, there are 2 possible spin values because each orbital can hold 2 electrons. Notice that there are 5 d orbitals, 3 p orbitals, 1 s orbital. So far we have 1, 3, 5. How many f orbitals do you think there will be? There will be 7 f orbitals, because their values range from -3 to +3. And again, each of these has 2 possible spins. And so, looking at all of the spins in the f orbitals, there are a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 spots. Does that make sense if there are 7 orbitals? Yes, because each orbital can hold 2 electrons. They will not always necessarily have 2 electrons in them. Many times there will be orbitals that will have no electrons or only have 1 electron, depending on how they fill in terms of energy. So in the fourth shell, there are a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 orbitals. So how many electrons total would it take to completely fill the fourth shell? It would take 32 electrons to fill in all of those orbitals, since each orbital can hold 2 electrons. Remember, make sure you realize that f orbitals cannot appear until the fourth shell. So the first shell has the first appearance of f orbitals. D orbitals have their first appearance in the third shell. And we've already gone over p's and s's. P's first appear in the second shell. S orbitals are there in the first shell and every single shell after that. That's also important to realize for all these other orbitals that once they appear, if you go to a higher shell, then those orbitals could possibly be there. Now, also as a reminder, the single s orbital is a sphere, a single sphere. That sphere will have layers in higher shell numbers or higher n, and the number of layers equals the shell number, and the number of nodes equals n minus 1. And these nodes are the places where the probability of finding the electron equals 0. So looking at the p orbitals, the p orbitals are shaped like dumbbells, and they lie along each of the axes. And so let me just color in this one that's pointing forwards and backwards. And the other two that are unshaded are pointing up this axis and along this axis. These 3 p orbitals, they all have a node right at the center, at the origin where these 3 axes are. And their number of nodes would still be equal to n minus 1. Notice the p orbitals don't appear until they're in the second shell. If you went to the third shell, these p orbitals would have more layers as well. Now, though, the number of layers in a single p orbital is also equal to n minus 1. But notice that there are 3 different orbitals. D orbitals start to have funkier shapes. There is one d orbital that is still pointing up and down the one axis, but there's this little extra ring of electrons, I should draw that forward there, that goes around the middle of the orbital, and I'm exaggerating this a little bit. The other d orbitals all start to have different kinds of lobe structures where those lobes appear in different quadrants. These are all in the plane of the screen, and they would be characterized with some sort of designation from those axes there. And as you use different axes to make those lobes, then they get different designations. And so with the p orbitals, we may have called these the pz, the px, and the py. These d orbitals are called things like dz squared, or dxy, or dxz, and they start to get more interesting designations. Finally, the f orbitals are going to start to appear like the d orbitals, but they have even more lobes. So the p orbitals had 2 lobes, the d orbitals had 4 lobes, the f orbitals are going to have 6 lobes in general, and they have even more complicated shapes. Thinking more about the shapes of the f orbitals and even of the d orbitals are really beyond the scope of Chem 1211 and Chem 1212. S and p orbitals are generally sufficient when you're talking about organic chemistry, which is where many of you will head after taking general chemistry. D and f orbitals you would learn more about in inorganic chemistry, which you would really only take if you were a chemistry major or working on a chemistry minor and choosing to take that class, or if you were interested in materials science and maybe you took that class as a physics major. And so the d and the f orbitals are really beyond the scope of this course in terms of thinking about their shapes, although the d orbitals will come back up again later in the semester when we discuss something called hybridization. The really important thing with the f orbitals especially, also with the d's, is that there are 7 f orbitals, and that those 7 f orbitals all combined can hold a total of 14 electrons.